Hey, Garrett, how are you?
Good.
Good. Now I have to ask, since I saw how well you drew yesterday, did you, the picture that you have as your profile picture, did you draw that?
No, I didn't, but I actually bought that.
Oh,
But I do have lots of drawings that I have done of that character that I
oh,
use.
really?
I
Man,
used to have I used to have my own drawings as a profile picture, but I bought that one and I really liked it.
oh, okay. That is really awesome.
Yeah, it was only $5 too, which was really good.
Oh, well, your drawing yesterday, all of that, that was amazing. I mean, like it looks like a real bottle of iodine. And that's really cool. You're very, very, very gifted. Um, you're the only person in math lab today, and so I didn't know. Let's see if I pulled it. I don't think I pulled up. I know that y'all have. There were. It was a worksheet. Let me see if I can find it.
Chapter 3 review.
Yes, sir. What was it called again? Remind me.
Chapter 3 review.
Okay. Chapter 3.
It's 25 problems.
Okay.
I just want you to know that I'm not really confident in this stuff, so.
Okay, that's fine. Then I'll just kind of work them out and we'll. Where? I know I just uploaded it just a minute ago. Review. No. Here we go. Oops. A lot of the, hopefully after we go through this, you'll be feeling more confident. There were a lot of concepts covered in this particular chapter. And I know sometimes people wonder, like, why is this connected to it? But, kind of when you start, at the very, very end, when you're simplifying equations where you have multiple radicals in them, and then you have to actually, square those and add like terms. That's a lot of the reason that you're doing some of this at the beginning. Okay, at the beginning here, you've got 28b to the fourth, and it's the square root, because if there's nothing in the check mark, it's an assumed square root. So I know that I have to factor that 28. And I've got 7 and 4, and 4 breaks down to 2. So I've got a pair of 2s. So you're looking, when you're finding square roots, you're looking for pairs. And once you find a pair, that is a pair of 2s. So there is a pair of 2s represented. And then there would be a 7 left inside. And now that is a b raised to the 4th. So that technically looks like this. And so that's 1 pair of B's, and that's 2 pair of B's. So you've got B raised to the 2nd power because there's 2 pairs. Another way to think about it is how many times will 2 go into 4? And it's 2, so you have that exponent of 2 on that B. And that's your final answer. Does that help a little?
Yeah, I have a question.
Yes, sir.
Is the second one xy square root 16y? Do you have the answers, or are you doing them as you go?
I'm kind of doing them as I go, but I can pull up the answers. So let me do that real quick, because that was pretty quick. But 16 looks right. X. So doing this would be 16x, y, and then y inside like that.
Oh,
Is
so
that what you?
16 on the outside. So 16x square root y.
Yes.
Okay, I was close. I put 16 on the inside of it, but
Oh, okay. All right. Let's talk about that for a minute. That's really great because students make this same thing, and same. It's like okay. Well, I pull once you pull it out, kind of what you're saying is that it's a perfect square, so it can come out of jail. That's how Miss Spell used to say it all the time. Once you've served your time and you're perfect, you can come out. It's a perfect square. So now you're no longer inside the radical jail, if you will. So, like, just like if I were to say 4, the square root of 4 equals 2, it's outside the radical now. So once you've figured out what the square is, it's outside the square root. So that's great. You're doing good. I'm kind of glad we're covering some of the more common errors because that happens all the time. So you are not alone. Let me pull it up. I still haven't gotten the answer sheet up. I just knew that one. Chapter 3, review.
I think I figured out 3 with Sparks.
You think you figured out 3 also?
Mm-hmm.
You don't even need me.
I will later.
Okay, what is it?
Is it 4y squared square root of 6x?
It is. It is. You are rolling. Good job. All right. I wonder if you think okay. All right. Now on this one, this is the one where you're combining like terms. And this is a weird thing. What you want to do is look at this and make sure that that is exactly the same. That's the most important thing when combining radicals, when you're adding and subtracting. Now, when you're multiplying or dividing, it makes absolutely no difference. Actually, multiplying makes absolutely no difference what's underneath there at all in any way, shape, or form. Makes no difference. You just go ahead and multiply what's underneath there. When you're adding and subtracting, it has to be exactly the same. And so there's a negative outside the first one. So that is like having a coefficient, if you will, of a -1. So you're really looking at this. This is -1 times the cubed root of 4 plus 2 times the cube root of 4. So I've got a -1 and a +2. So if I combine a -1 and a +2, I get a +1.
So it's C?
Yes, sir. Now on number 5, I have to go ahead and factor those out. And I'm looking for cube roots this time. So I would be looking for sets of 3 instead of pairs of 2. I have to have 3 of something before it's quote unquote served its time and able to come out of the radical. So 54 is 9 and 6. So I'm looking for sets of 3 because of what's in the check mark there. And I only see 1, and that's a 3. So that's going to be 3
Cube root of 2.
Cube root of 2. Good job. And if you'll notice, there's a negative outside there. So that's like a -1. So that's -1 times 3. So that's going to make that a -3. Now, with regard to 32, we'll factor that one. Once again, we're looking for sets of 3. Oops, I just want to take the 32. We're looking for sets of 3, 8 and 4, 1, 2, 3. There's one set of 3. We didn't quite make a second set of 3. Didn't quite get there. So we've got 2 times 2 left on the inside. So that becomes 2 times the square root of 4. 32 does. Cubed root. I'm sorry, not square root.
Is it negative?
And because there's a negative out front, it'd be like multiplying that by a -1. So yes, sir, it is. Minus 2 times the cube root of 4. And this is essentially the same thing. So I'm going to multiply this 2 times that 3 also. So that's going to be minus 6 cube root of 4. So now I want to combine like terms, and these are the only two. So I've got -3 cube root of 3 of 2. I mean cube root of 2 minus 8 cube root of 4, which is B.
But B is positive 3 cube root of 2.
Ooh, it is. Oh, you know what? Thank you for pointing that out. And that makes me know an error that I made. So my apologies to that. Do you notice the negative inside there? I forgot to address that when we were factoring.
Oh, it cancels out because it's a negative inside of it.
Yes.
Okay, that makes
sense. And
sense.
I forgot to point that out. I'm so glad that you got it as quickly as you did, because I didn't mean to confuse you, but I should have made one of, and you can have a negative when it's a cube, because -2 times -2 times -2 would still be a negative, and that's why you can have a negative inside a cube root.
That makes sense.
Oh, good. I'm so glad. Bless you. So that we would have had, what we would have pulled out, a -2, isn't that right? Yeah. So a -2 times, or -3 times, we pulled out a 3. So a -3 times a -1 would make that positive. So good job. Good check. Way to go, Garrett. You don't need me really at all, but I appreciate you coming to Math Lab. Okay, so now, just like I said, 4 and 5, we had to pay attention because you have to add or subtract like terms. But when you're multiplying, it doesn't make any difference. You can just combine what's under the radical by multiplying. So now this becomes 3 times 8 is 24. And we've got the square root of 24. So when we factor that, that's 4 and 6 and 2. So we can pull out a 2 because there's a pair of 2's. So that's 2. And then I've got this 6 left. So 2 times root 6.
Well, that makes sense.
Not too bad. And then on number 7, you multiply 12 times 12, and you could do it that way and get 144. And this, we know the square root of 144 is 12. But another, I'm sorry?
What's B?
Yeah, so it is B. But another thing, remember when we rationalize denominators, and we actually do that, and we're going to do that in the next step? We always multiply it by the matching thing. So we know that that would just be 12. Now, on this one, what I'm going to have you do is, when the number is that big, it is my suggestion that you go ahead and factor things out. And the reason why I say that is because you don't want to deal with really big numbers at the top. So I would go ahead and do my factoring first on this one. So we're taking this, we're looking for perfect squares. So we've got actually 16 and 3, right? And 4 and 4. So you have the perfect square of 4. And then you can take that out, and you've got a root 3 in the bottom. And lo and behold, look what happens. You've got 4 root 3 over 4 root 3, which really equals 1. So you don't have to do anything else. Like that. Does that make sense?
Yeah, it does.
Okay, good. Okay. Now, on number 9, well, you can automatically cancel out the 5 and the 5. They just go away because that's being multiplied, so they can cancel each other out. But on the 45 on the bottom, you would factor it, and you have 9 and 5. And so you can take a perfect square of 3 out because there's a pair of 3s. So I have the square root of 10 over 3, and then this is left, so that's square root of 5. So now I have to rationalize the denominator by multiplying by that root 5 on the top and the root 5 on the bottom. So that gives me root 50 over, and then that's going to be root 5 times root 5 gives me a 5, and 5 times 3 is 15. And now I have to factor that 50, which factors to this. And I've got a pair of 5s that I can pull out. So that's going to be 5 times the square root of 2 over 15. And then this actually reduces to root 2 over 3. I don't have, yes, I do. I was like, I don't have that anywhere. And I couldn't find it in the answer bank.
It was B.
Yes. Did you track with that? Did that make sense?
Yeah.
Okay. Because I know there was a lot going on with that one. Did you get everything copied down?
Yes, it did.
Okay, cool. All right. Write each expression in exponential form. So all you're doing on these is whatever is in the check mark is the denominator of the expression. So that we're going to write 5p raised to the third power, or that like raised to, and that's going to be an exponent. And if it's not like if it doesn't have anything on the outside, there's a 1 that's understood, and that's your numerator. So it's going to be this. For number 11, you write your n, whichever is in the radical, and whatever is in the check mark, that's your denominator. So that's 2. And then the power on the outside is the numerator. So that's 3. Write each expression in radical form. So now, undoing that, we know we're going to be in a radical, and we're going to put whatever's inside the parentheses inside the radical. Whatever the denominator is the power, and this happens to be a 2, so that's the square root, so we don't have to write anything there. And it's also, the numerator is also a 1, so it's not going to be raised to an additional power. So the answer is B. Is that what you said?
Yeah.
Okay, cool. All right, so for 13, you're going to write what's inside the parentheses underneath the radicand. And then what goes in the check mark is the denominator. So that's the 5. And then that's raised to the third power.
Missed that big time. Oh, I swapped it around. Sorry.
Oh, that's okay. That's okay. You caught yourself. It's better to catch yourself today than tomorrow. That's the whole point of the review. So there it is. And there's, like I say, there's some moving parts in this. So the denominator is the check mark, and the numerator is the power that it's your answer is raised to, essentially. Okay, simplify these. When you have a power raised to a power, you're multiplying. And this particular one then is also a negative. So that means that it's going to be pushed to the denominator. Okay?
Mm-hmm.
But what this is the cube root of A raised to the, this reduces, though. How many times does 3 go into 24?
Excuse me?
This reduces. How many times does 3 go into 24 is what I asked.
Oh, sorry, because my mom was coming in the room for a second. I was.
Oh, that's okay.
Attention.
So it's A to the negative 8, and the negative pushes it to the denominator. So it looks like that.
Okay. Okay, I get it now.
Okay. So this one, I have to be careful on this one. That 1/2 is going to be distributed to both the 4 and the 6. So now that would look like 4 to the 1/2 and x to the 6/2. So this reduces and looks like that. But this can be simplified even further because this is the same thing as the square root of 4. So what's the square root of 4?
2.
So your final answer is this.
Couldn't you just half the 4 and half the 6?
You could. You sure could. However, it's easiest for you to think about. That's absolutely, yes, you could. The only thing I was trying to do is also, and it's great that you can think quickly like that. That's awesome. I was just trying to show that you just make sure that you distribute everything to the inside of that parenthesis. All right. Solve each equation. The square root of x equals 9. So the first thing that you're going to do is square both sides to get the x from outside the radical. And if you check your answer, if you take the square root of 81, it does equal 9. So it is true.
Can you give me just a second?
Yes. Hey, Alex.
Hey, Mrs. Sparks.
How are you, sweetheart?
I'm good. How are you?
Good. Is there something specific that you came for?
Yeah, I had a few questions about the problems on the Thanksgiving review.
On the Thanksgiving review. Let me make sure that I load it up, okay?
All right.
This is the one, right?
Yes, ma'am.
Does that look like it? Okay, good. Which one did you have a question on?
I had a question on number 9. I was wondering how to do that one.
Oops, I just
I had
wrote
a
on.
question on a few of them actually, but 9 was one of them.
Okay. Oh, that's fine. That's what I'm here for. Okay, number 9. What you're going to do on that is I would start with this right here and multiply those two together. When it's a power to a power, you're going to multiply. Okay? So x, y to the 3/2 times y, and then 2 times 5 is 10, and 3 times 4 is 12. And then down here, x doesn't change at all because it's not being added to anything, but we're going to add 3/2 and 10/12. So you have to get a common denominator of 12. 2 goes into 12 6 times. 6 times 3 is 18 plus 10 over 12, which gives me 28 over 12. And 4 goes into both of those. 4 goes into 28 7 times. And 4 goes into 12 3 times.
Okay, that makes sense. I was doing the exponents the wrong way with the y.
Oh, okay. All right. Lots of good rules to remember.
Yeah.
Okay, what's another one?
Another one was any one of numbers 33 through 36. I was a little confused on.
Okay. And all I can tell you is number 40. No, not number 40, number 41. I have done on a separate sheet of paper, but it's even longer than 39 and 40.
Oh, wow.
Yeah. And it's really, really long. So I'm going to tell you in math lab that you can eliminate number 41 after Mimi Chapman had gotten it to a certain point, and then I worked it with her. Then I had to finish it. And I tried factoring, and then I defaulted to the quadratic formula. And then I found out that Miss Murphy had done the same thing, and so had Miss Wynn. But the numbers are like literally one of the numbers, once you're multiplying some things out, it's like 16,900 or so. I'm not, maybe not quite that big, but they were big. I can't remember them right off the top of my head. So you have my permission to eliminate number 41. It was horrendous.
Okay, thank you.
Uh-huh.
I was like trying to work that one, and I was like, man, I'm gonna have to ask about this. I'm kind of confused. Like, I was like, this thing's going on for a while.
Yeah, it was definitely, only a math geek like me would enjoy a problem like that. I think Mimi, in her sweet little polite way, was looking at me like I was crazy for assigning it, and she's probably right. Anyway, so any of them 33 through 36, is that what you said?
Yes, ma'am.
Okay. All right. Garrett, are you still with me?
Yep.
Okay. We're going to get back to your worksheet in just a second.
Okay.
Number 33. On this one, the very first thing, and I talked about this a little bit in class yesterday, but my recommendation is to always work PEMDAS in reverse. So what you want to do is, in an equation like this, you want to look at, is there any adding and subtracting going on? And in this particular one, there is not. So now you're looking for multiplication and division. And then your exponents and your parentheses or groupings comes last. But there is a 4 being multiplied to this grouping that's being raised to a power. So what you want to do is to divide both sides by 4. And that's your very first step. And a lot of times when the problems get really complicated like this, I always even will write PEMDAS on my paper and write this little arrow to remind myself that's what I need to do. So I'm going to divide everything by 4. And that leaves me x minus 20 on this side, raised to the 3/2. And then this gives me 5/12 on this side. And now what I'm going to do is multiply both sides by, raise them or multiply this rational exponent by its reciprocal to clear it, just like clearing a fraction a long time ago. But whatever I do to this side of the equation, I have to do to this side of the equation. So while I made this side, the left side, pretty, I made the right side ugly. But what we're going to do now is think about what radicals mean. Think about what rational exponents mean. This means we're taking the cubed root, because the denominator is what goes in the check mark. The cube root of 5/12 raised to the second power. So what you're going to do is take, what is the cubed root of 5/12? I should know this off the top of my head, but I really don't. And I've done it so many times too. So it really tells me I should know. 8. So this is going to be 8. So the cube root of 5/12 is 8 squared. Okay. So we've got x minus 20 equals 64. Then you're going to add 20 to both sides, and you get x equals 84.
Okay.
Did you get that before I start erasing everything? Sorry.
No, I got it. Yeah.
Okay. Would you like me to do another one of those?
I think I'm good with those. And then I got number 40 almost all the way down. So do I just have to use quadratic to like figure out the answer?
I don't think on 40 I had to, but let me go back over it. Is it still written here? Oh, oh man, I think I closed it. I had it. It literally took 2 pages. I think I did it. Hey, Garrett, do you remember if I did it the other day? Is he still with me? He might have gone to do something else while he was waiting on me. I'll just rework it. But I actually think I had to do it on another sheet of paper. But Brooke Williams said she was able to fit it all on the side. But I don't know. I don't trust myself to do that.
Yeah, I was working it out and I got a while. Like I think it was like at least a half a page.
Yeah. Let me see what comes up when I pull this up. Oh, here's part of it, but that was just my answer sheet. That's just me. That is actually me checking the solutions because only one checked. I was hoping it would ask me if I want to open a new copy. That's what I'm trying to get it to do.
Technology is really annoying sometimes.
It is. It's not going to let me, and I just really don't want to erase. This is my check, and I don't want to erase it. Oh, well. And Miss Binger and I were working yesterday on trying to figure out how to clear all, and there's no way to do that either.
You'd think they'd have a button for clearing it all, though, because it's like...
All right. But they don't. And this takes an entire page. Would you mind reading me the problem?
Oh, yeah, sure. It's 4 minus a all under a radical.
Okay.
Minus 7a plus 4 all under a radical.
Okay.
Equals -4.
Or minus, right? Or, oh, no, the equal isn't there. This was minus?
Yeah.
My bad. So did I write it right?
I think it's a -4 after the equal sign. But other than that, it's right.
Okay. Thank you. All right. So what I'm going to do is I'm going to go ahead and get this radical over on the other side. I shouldn't have written that. I'm going to get the 7a over to the other side, so that when I'm squaring it, because I could square it on this side. That is definitely an option. You could do that, but you're going to be foiling two rat things under a radican. And my preference is to just have one of them when I'm foiling. And when I say that, I mean because they're going to become binomial expressions. You've got 7a plus 4 minus 4 under the radical. So now I'm going to square both sides. So this just becomes 4 minus a. And this side technically looks like way up here, 7a plus 4 minus 4 times root 7a plus 4 minus 4. That's what that is. So you've got to FOIL this. All right? So foiling it, it comes out and looks like this. So technically now I've got -4 times this. That's my outside. So that's going to be -4 root 7a plus 4. And then the inside is the same thing, which is -4 times, oops, I ran out of room. I'm just going to back this up. -4 times root 7a plus 4. And then -4 times -4 is plus 16. So now I can combine like terms, which are these two right here. So now I have this line, 4 minus a equals 7a plus 4 minus 8 root, because -4 plus -4 is -8. 7a plus 4 plus 16. Now, once again, I'm going to combine like terms again because I've got this +4 and this +16. And you might have done all of this in one step, but and now I want to move my 7a to the other side to combine like terms from this side to the other. So that's going to give me 4 minus 8a equals -8 7a plus 4 plus 20. And I want to combine this -20 to this side. And then I'm going to square both sides again. Was this, and this is number 40, right?
Yes, ma'am.
Oh, Jesus. Okay. Have you seen that I did anything wrong so far? Because I'm like, I don't remember this. This is really bad. I'm running out of room too on top of that.
Oh, I think the 24, the -24, I think that needs to be a -16.
It's 16. Thank you.
You're welcome.
I knew I did something wrong. Doesn't fix it a lot, but it helps. You know what I think I'm going to do? I don't think this breaks any rules either. I can't think of any rules that this breaks. Instead of squaring both sides first, I think I'm going to divide both sides by -8. That'll make this prettier. And now square it. Well, I just don't have enough room to write anything. I'm sorry, Alex.
That's all right.
I'm trying to write this, but it's so, if I'm squaring this right now is what I'm doing. That's the side that I'm working on. And so I'm going to turn this around. And I'm also going to subtract 7a from both sides at the same time. Will that be confusing?
No.
And then subtract 4. And that actually cancels out that 4 and leaves me a 0. So I subtracted 7a and I subtracted 4. And so now I have a squared minus 3a equals 0. And then I can factor an a out and have a minus 3 equals 0. So a equals 0 and a minus 3 equals 0. So a equals 3 or 0. And this, please tell me. Maybe I'll use this. That was my check, and hopefully I haven't written over it. The check that I had just a minute ago. Oh, goodness. Hopefully I can find it. I probably won't be able to find it now. But I had the check up just a minute ago where I checked it. The 0 does not check out. And I'm not going to be able to find it now. But when you plug all of this back in here, the 0 does not check. Only the 3 checks. So your answer is this. The 2 answers that you come up with are 3 and 0, but 3 is the only one that checks. Okay. Did that answer your questions?
Yeah.
Okay. Do you have another one on the review?
Not on this review now.
Okay. Did you have some with regard to the textbook?
Yeah.
Okay. Well, let me do a few more for Garrett, and then I'll come back to the textbook. Is that okay? All right, Garrett.
Yep.
Did you try number 17 by chance? Huh?
No, I did not.
Oh, okay. All right. So the first thing you're going to do, kind of like what I was talking about with Alex, if you can, you want to do PEMDAS in reverse at any point. And here we can divide both sides by -7 first. So we get the square root. If you divide both by -7, you would have the square root of p equals 9. And then you square both sides. And you get p equals 81. Seems to be a theme.
But why would you do it that way?
Did I do that wrong? Because if I square it, I'm going to end up with like really, really big numbers, first of all, because I would have -63 squared. And eventually I'm going to have to divide by that anyway, because you want to get it down. You want to work PEMDAS in reverse always. And if you'll think about it, there's no adding and subtracting, but there is multiplying and dividing. And even though it's not, this p is technically, even though it's not written as an exponent like this, it's technically this, p raised to the 1/2, because the square root of p is the same thing as p raised to 1/2. So you're not going to deal with an exponent until you deal with multiplication and division. Does that make sense?
Yeah.
You're always, when you're breaking down an algebraic equation, you want to work that PEMDAS in reverse. Does that help a little bit?
Mm-hmm.
Okay. Okay, so now solving these equations. Once again, working PEMDAS in reverse. I think this was on the other one too, wasn't it? Was this the same thing? Alex, are you still here? Did she leave?
She still
Yeah,
shows up.
I think. Oh, not quite the same thing, but look how close it is to number 33. It's really close. So I'm going to divide both because I'm going to divide both sides by 4 because I'm working PEMDAS in reverse. There's no addition or subtraction, but there is multiplication and division. And to undo this, I'm going to divide both sides by 4 and get 512 equals x raised to the 3/2. And to get rid of the 3/2, I'm going to multiply both sides by 2/3. Multiply, actually not multiply it, but raise it to the 2/3 power. And a power raised to a power, you multiply. So this actually eliminates that. But now I have 512 raised to the 2/3, which the cubed root, that's the cubed root of 512 raised to the second power, which is 8 raised to the second power, which is 64. So x equals 64.
It makes more sense now.
Okay, good. All right, so the inverse of each function. I kind of talked about this the other day in Math Lab, that I have those Mrs. Sparks confident building steps on inverses. I always rewrite the problem. Equals 4x plus 1. And then I change my fancy g of x to a y. And now I swap my x and my y. Those are the steps that I know I can perform almost every time. And so I kind of talk about them as my confidence building steps because I feel like I kind of get on a roll and I'm feeling more confident that I can actually do it. Now I'm going to begin that whole process of working PEMDAS in reverse, but I'm solving for y. I'm trying to get y all by itself. So I'm looking, is there any adding and subtracting going on? And there is. So I'm going to subtract 1 from both sides, and I have x minus 1 equals 4y. And now I'm moving to multiplication and division. So I'm going to divide 4 by both sides. So now I have y all by itself, and it's y equals x minus 1 over 4. And I'm going to rewrite it back into the inverse function notation. So it's x minus 1 over 4.
Okay, that makes sense too.
Okay, good. All right. You weren't supposed to say those. Sorry about that, Math Lab people. My children are peeking into bags, and it's Christmas time, and they're not supposed to be. All right. So once again, I call these my confident building steps because I'm like sometimes just staring in a problem, you know, you get that almost that writer's blank. and you're like, okay, what do I do next? So if you just kind of start writing, sometimes your brain kicks into gear. So I rewrite the problem, and then I switch my fancy function notation to y equals 5, or root 5, the fifth root of x plus 2. And now I swap places with my x and my y. And now I'm going to start working on that whole PEMDAS in reverse. So I'm looking for any adding and subtracting. And there is some adding going on. So I'm going to subtract 2 from both sides. So now I have x minus 2 equals the fifth root of y. And now I want to raise both sides to the power of 5 to get rid of that fifth root. So now this is going to be y, because this cancels that out, equals x minus 2 raised to the fifth power. And then I go back to my fancy inverse function notation as my final step. And I see that it's B. So I kind of begin with those confidence building steps and end with those. All right. Making more sense?
Yes.
All right. How are you on all of these? Are you good on these? Anyone? I'm sorry?
The last page is probably what I need the most help with.
Okay. All right. Okay. So on this one, what you're going to do is just take H and add G. So 4t plus 1 plus 2t minus 5. So you're going to add 4t and 2t. So that's going to be 6t. And you're going to combine 1 with negative 5. So that's going to be minus 4.
But what about the t on the outside?
That tells you what the function is defined at. And both of them are already defined.
I kept getting confused. I think I had to multiply t. And I was like, wouldn't it be 6t squared? I was like,
no, That just tells you what you're subbing in for the variable. So that
it looks like it's distributing, and it's really confusing.
It is. And function notation, to be perfectly honest with you, doing the functions themselves are never really that hard. Understanding function notation is probably the most complicated aspect of it, because all of the notations are so very different. So understanding those, because those are all on the ACT, SAT. So understanding what it's asking for is really what the learning curve is. It's not doing the math. The math isn't that hard. In interpreting the syntax is the most difficult part. So like on number 2, notice that that looks a little similar, that G composite H looks very similar to multiplication. However, it is not. In our books, that same notation looks like this. That is supposed to be an H. And that is an N, and they look eerily similar. But the book uses this notation. And I really want to say the SAT uses one and the ACT uses the other. But this and this are the exact same thing. So what this means is H defined at N, which is N squared plus 5, stuck inside G. So anywhere that there's an N in G, I'm going to stick this N squared plus 5 inside it. And now I'm going to distribute the 4. That's 4n squared plus 20 plus 5. Then I'm going to combine like terms, and it's 4n squared plus 25.
Thanks for clarifying that. I had no idea what that meant.
No problem.
Is that going to be on the test?
I don't know if there's a composite on it or not. I cannot remember, but just please remember that it could be written in either of these notations. I can't, I don't know what, and I don't know what her test looks like either. I think there's a composite on mine, but I think it's written in this notation. All right, now on number 23, that's G divided by F defined at X.
Is it C? Ms. Parks, you muted yourself.
Yes, I'm sorry. My children were asking me a question. They were trying to run to the store and Mackenzie's car wouldn't start. So
Okay.
I was sorry. I was handling a little family crisis. I'm sorry. But and I have one of those boxes that you can myself accidentally now. I'm not even trying to. Okay. Did you say number 23? What did you say the answer was? C? It is C. And if they by chance, which I don't think she's going to, if she asks what the domain, if the domain is limited on something like that, which I don't think she's going to, remember, it will be all real numbers except whatever makes that denominator 0. So if you actually have to find what that is, you just set that little tiny algebra problem equal to 0 and solve for X. And so for this one, it would be 3/2. So it would be all real numbers except for 3/2. I don't think I don't think that's on there, but I just wanted to make sure I covered it just in case. Okay. Because you can't have a 0 in the denominator. It's a no. Okay. And number 24 is actually multiplication. But this was interesting. Because Miss Wynn and I actually had to talk about this. So what you're doing is defining both of them at the number 1. So you'll plug in 1 into both of them. I think. Yes. Right.
Everywhere there's an X, I put a 1 there.
Yes. And then multiply them.
So it's A?
Yes. And then this one, just square both sides. And you get 15 minus X equals 3X minus 5. And solve it like any other algebra problem. And then subtract 15 from both sides. And then you're supposed to plug that back in and make sure it works.
It does end up being 10, both sides.
There you go.
Thanks so much, Miss Sparks.
You're most welcome. Have a blessed day.
You too. Bye.
Bye. Okay. Are you still with me, Alex?
Yep.
Bless your heart. Did you learn some stuff, though?
Yeah.
Praise the Lord. Thank you for waiting patiently with me.
You're welcome.
Let's go into the workbook. Did it load? Okay. Which one?
They're all on page 179. There's just 3 of them though. It's numbers 6, 10, and 13.
Oh, okay. So I figured it was going to be the test. I'm so sorry.
That's all right.
I assumed.
I was looking back and I realized that those 3 I kind of like stopped in the middle and was looking back over them and I was like, yeah, I don't know what I was doing and I don't know what I did do.
Okay. And what numbers were they again, love?
6, 10, and 13.
6, 10, and 13. So x to the 5th equals -10. Okay, were these the ones that you were, I think you were supposed to, I was thinking, okay, no. I was like, were we supposed to use the calculator? Because this is kind of closer to the beginning. And sometimes you were supposed to use a calculator and sometimes you weren't. And then you are supposed to use your calculator on this. But the first step in the equation is to multiply both, like raise both to the power of 1/5. So you would have the 5th root of -10.
Okay.
And then that you would plug into your calculator.
Okay, so it's that simple.
Or you could just raise it -10 raised to the 1/5. I think that's easier to do in your calculator because then you don't have to go to the math function.
Okay, I think what threw me off was the negative. Like my brain just saw negative and was like, you can't have that under radical. What am I doing wrong?
Oh, yeah, but in an odd radical, you actually can. It's only even radicals you can't, but odd radicals you can. But all you would do is take -10 and raise it to the 1/5 power. What is your answer, by the way? If you do that.
I don't think I finished working that one out because I think I got confused with the radical and was like,
oh, I know. Do you have your calculator in front of you though, by chance?
Yeah. I got -1.58.
Okay. I can check the answer for you, but that sounds about right.
Okay.
Hang on just a second. I'm looking it up because remember my calculator died and I still haven't gotten a new one yet. So I'm just gonna look and see what it is for us real quick. And then it was 6, and then I think you said 10. Is that correct? Yeah. Okay. I'm going to confirm 179. I'm going to confirm our first answer, and then I'll write that one out. Did you say -1? -1.58?
Yeah.
That is it.
All right.
And then if I switch over to this blank screen, well, semi-blank screen, would you mind again reading? Actually, I don't think you need to. I've got it on my other screen, so we'll be okay. I so wish there was a clear all.
Yeah, instead of having to keep on pressing undo.
Yes. Or taking my stylus and like scribbling on the screen, because then sometimes the stylus just gives out and
Yeah.
doesn't keep erasing. So it's just like, oh my goodness. Okay, so I'm going to kind of start talking you through this one, since obviously the erasing looks like what you're going to want to do on this one. The easiest thing to do, because the radicals, it was good that you paid attention. The radicals aren't the same. So you can't really do any combining on those. And, you know, it's interesting because I was telling Garrett earlier that you could combine radicals. You could always multiply radicals, but here's a situation where you can't, because the little what's in the check mark doesn't match. So on number 10, it's number 10 with lots of 10s in it.
Yep.
You would want to rewrite these with rational exponents.
Oh, I see.
And then multiply.
Because then you can combine those.
Yes.
And you'll get 10 to the 5/8, which is also the...
Oh, I didn't even think. Yeah. Well, you get 10 to, yeah. This one actually reduces to 10 to the 4th, because 8 times 1/2 is 8 halves, which is the same thing as 10 to the 4th. And then this is the cubed root, or here, there's a couple ways to do this, and I don't know which. 3 goes into 8 2 times with 2 left over. So here's another way to do this. Like that. Does that make sense to you?
Yeah.
Okay. So now I've got 10 to the 6th. Did you do this already? And that's why I think you might have already said this out loud to me. So then they actually have the final answer if you look at this at the back of the book, but maybe you don't have it. It's 1, 2, 3, 4, 5, 6. And then they have it times the cubed root of 100 as the final answer.
Okay. So it'd be 10 to the 6th times the cubed root of 100.
Yes. Does that make sense?
Yeah, I was just overthinking it, I think.
Okay. All right. And what was the other one?
Number 13.
13. Yeah, these in all honesty, it's kind of they look a little ugly and kind of daunting. So and like I think I've said this in class a lot. These types of problems, each one you kind of have to look at as a new situation and remember all of the rules and moving and manipulating things around. And I think, you know, like, okay, what's going to work best in this situation? Like on this particular one, it worked best to change it to fractions, you know?
Yeah.
And work it that way. So number 13. So you have 2 square root of x times the square root of x to the 3rd all over the square root of x to the 15. So the first thing I would do is work my grouping at the top and combine as much as I could. So I can take that x times that x to the 3rd, and I can combine those to be x to the 4th. over 64x to the 15th. All right. And then I can take, this can come out and it becomes x squared, because the square root of x to the 4th is x squared. And down here, I can take the 64 out because that's going to be 8, right? And then x to the 15th, how many times does 2 go into 15? Because you're taking the square root. So how many pairs?
7.
It would be 7,
right?
with 1 left over. Because how many pairs of 7s pairs of x's can come out is kind of another way to ask it. Does that make sense?
Yeah.
Okay. So now I can't leave a radical in the denominator, right? Because that's a no-no. And the other thing, I can actually cancel that out. So that's going to just leave me with an x squared and then a 4x to the 7 with a radical of x. The other thing I can do is it's 2 minus 7, right?
Yeah.
Okay, so now I've got a 1 on the top with a 4x to the 5th with a radical of x. And I can't leave that radical on the bottom, so I have to multiply the top by the square root of x and the bottom by the square root of x, which gives me root of x all over. And then this is going to give me another x, which I add to the x to the 5th. So it's 4x to the 6th. Does that make sense?
Yeah.
Okay, good. Were there any other questions?
I think that's it.
Okay. Thank you for waiting so patiently.
Well, thank you for helping me.
Oh, no problem. You have a blessed afternoon, and I'll see you in class tomorrow.
All right, you too.
Bye-bye.
Bye.